Hi, everyone. Sorry to be missing you today, but I'm sure you are in more than capable hands. We're going to go ahead with a lesson that actually should come a little later in the week. I've had to rearrange some things for this week for you guys in particular. So we've been practicing a lot of different types of factoring, right? And we will be taking a quiz over all of that factoring on Wednesday, but I felt like you guys in particular needed a little bit more practice with the factoring before I quizzed you on it. So instead, I'm going to jump ahead to this lesson. This is the Factor Theorem, which is lesson 11.5. And I'm really hoping today to answer the question, why are you making us factor over and over and over again? Ignore that. Why are you making us repeat this process over and over and over? Why is it so important? That's hopefully what I'm going to convince you of today, maybe convince you of. So just so you have an idea of what's going on for the week, we're going to cover this lesson today and then another lesson tomorrow. Neither one of those lessons will be covered on your quiz on Wednesday. So we're kind of leapfrogging over your quiz to cover a couple of the other lessons in this chapter. Wednesday's quiz will cover the polynomial stuff and all of the factoring we've been doing. And then Thursday you will have another blended lesson that is really more of like a review day. And then when I see you again on Friday, we will just kind of touch base on everything, all of the homework and everything, these last couple of lessons, stuff like that. So Friday will be a big pull it together day, okay? But without further ado, make sure that you are, in this section in your notes, the factor theorem. These first couple of things we're going to talk about is just sort of preliminary information, especially since we skipped over lesson 11.4, which talks a little bit about zeros, so we need to make sure we kind of fill you in on that. And then also anything that I'm doing on my calculator today, I really strongly encourage you to do along with me, okay, so that you're seeing it yourself. Okay, let's get rid of me. There we go. Okay, so we're going to start this lesson on the factor theorem by talking about a property that actually is a pretty basic algebraic property. You may have seen it before. It's called the zero product theorem, or also known as the zero product property. And what this says is if you have two things being multiplied together that are equal to 0, then what you have to know is that A equals 0 or B equals 0. Essentially, that's saying that if two things multiply to make 0, one of them has to equal 0. That's the only way to get 0 from multiplication, is to actually multiply by 0. Okay? And that's going to be important when we get into the actual factor theorem. But for now, let's just write that down so we have it to refer back to. And then the other thing I want to talk about is a 0. Now, this is different than like the number 0, but a 0 on a graph is the place or a value of x that gives a y value of 0. So if we think about like this function right here, the zeros would be the values of x that I could plug in, and it would make the whole thing come out to equal 0. Now, when we think about this on a graph, if we're making y equals 0, that's going to be somewhere along the x-axis, right? So like you might have a 0 located here, or a 0 located here, or a 0 located here, because those x values are making your y value equal to 0. Y is equal to 0 anywhere along the x-axis, okay? That means a 0 is really the same thing as a root or an x-intercept. And I want to throw one more your way. It's also the same as what's called the solutions. And that will come to a little more later this week. Okay? But I want you to know that those words are kind of all interchangeable. Roots, x-intercepts, solutions, zeros, all of those mean the same thing. Okay? It means these points on the x-axis. Okay, and the whole idea today is to relate zeros back to factors, okay? So let's just dive into example 1 here. It says graph this polynomial on this particular window. Use the graph to identify the zeros. Okay, so I'm going to go to y equals, oh, someone's got something else in there. I'm going to go 2x cubed plus 2x squared minus 24x. I'm going to go to my window and I'm going to set it so that my x's go from negative 10 to 10. So that's already there, negative 10 to 10. And my y's, I want to go from negative 50 to 50. So it looks like whoever was using this before me already had it set. And then I'm going to hit graph. And this is what I see. And I want to just use this graph to visually identify where those zeros are located. And I'm just going to kind of sketch this on my paper so that I have it. This picture looks something like this. And I want to know, where are these points located? Okay, well, just counting here, counting dots, this one looks like it's at -4. This one crosses right at the center, so that crosses at 0. And then this one crosses at +3. Okay, and again, I'm just counting dots along the x-axis there. Okay, so my zeros are located at x equals -4, x equals 0, and x equals +3. Okay, now let's backtrack, go back to that original polynomial, and it says to factor this polynomial. Okay, so factoring, that's just what we've been doing all this week, and the first thing I would always look for in something like this is a GCF. So I see that I can pull out a 2 and an x from everything, and that's going to leave me with an x squared plus a 1x minus a 12. Okay, so that was just me taking out a GCF. And then I'm going to take these parentheses and go one step further. This is negative, so that means I know I'm going to have one positive and one negative, right? Because that's how I multiply and get a negative. And now I want to multiply to make 12 and add / subtract to make a 1 in the middle, right? So when I think about all the ways there are to multiply to 12, let's see, we could go 1 and 12, we could go 2 and 6, we could go 3 and 4. I think this is where I'm going to be able to make a 1, right? So I'm going to go +4, -3, and then bring down my 2x. So now what I want you to see is that I have 3 factors, and up here I had 3 zeros, okay? And they are related. What we can do is we can use that zero product property that we talked about up above. And since this is now multiplication, right? This is something times something times something. If I wanted to find the zeros, meaning I wanted to make this thing equal 0 at the end, then I know that either 2x would have to equal 0, or x plus 4 would have to equal 0, or x minus 3 would have to equal 0. Okay, so just let that sink in for a second. I wrote this thing as a multiplication problem. I wrote it as this times this times this, right? And I want it to be equal to 0. That's how I find zeros, is by setting it equal to 0 and solving, okay? So if this times this times this has to equal 0, then one of these 3 things has to be equal to 0, okay? So these are my choices. If 2x equals 0 and I divide both sides by 2, I get that x equals 0. If x plus 4 equals 0 and I slide that 4 over to the other side, I would end up with x equals -4. And if x minus 3 equals 0 and I move that -3 over, I end up with x equals +3. Lo and behold, look at these compared to these, okay? You should find that what we just found were the zeros algebraically from the factors. Once I had the factors, finding the zeros was no problem at all, okay? And so that leads us to something called the factor theorem, okay? And the factor theorem, I'll go ahead and write it in words and then we'll dissect it. It's an if and only if statement, meaning it can go in both directions, but it says f of a equals 0 if and only if x minus a is a factor of the polynomial f. Okay? F of a equals 0 if and only if x minus a is one of the factors of f. Okay. So just to dissect this just a little bit, just so we're clear, this notation right here is really saying that a, whatever number a represents, is a 0 of the function, otherwise known as a root, okay? So we can say that a number is a root if and only if x minus the number is a factor. And the reason for the x minus is because we're going to end up doing x minus a equals 0, moving this to the other side, and we would end up with x equal to a, okay? Which is what this is saying up here, okay? So that theorem, because it's an if and only if, it can work two ways. What we just did a second ago is we said, hey, we know the factor is x minus a, okay? That was a factor. And we use that information to find the roots, which is x equals a. Just so you know, when we get down here, we can go back the other way. We can take the roots and turn them into factors as well. And the sooner you get kind of this circular relationship, that every time you have a factor, you have a root, and every time you have a root, you have a factor, the better off you'll be in terms of this stuff, okay? Okay, let's go ahead and put that into practice. Let's do example 2, and maybe once we apply the theorem, it will help you understand it a little bit better. So looking at this one, it wants me to find the zeros by hand. Well, finding the zeros by hand really means that I want to use factoring. Okay, so I have to factor this thing. So I'm going to start with a GCF, and it looks like I can pull out a 3 and an x cubed. And let's see, that's going to leave me with, divide by 3, and I get 2x squared, 5x minus 12. Yep. And now this needs to break down further. So remember, this is where I go 2 times negative 12, and I get negative 24. Let me write this. And now I need numbers that multiply to negative 24 and add to 5. Okay, and if you need to, you can make a list of all the ways to multiply to 24. But I'm going to go with 8 and negative 3. Okay, that's how I'm going to make a negative 24 and a positive 5. So then I'm going to rewrite this thing with my 3x cubed still out front as 2x squared plus 8x minus 3x minus 12. I'm going to pull a GCF from each half. So I'm going to pull a GCF from here and a GCF from here. 2x, and then I end up with x plus 4. Here I'm going to pull out a negative 3, and that will leave me with a positive x and a positive 4. Okay. And then I'm going to pull this parenthesis and say this is x plus 4 times 2x minus 3, and then put my 3x cubed back in front. Okay, so this right here down at the bottom, this was me factoring. This was all the stuff that we did last week and, beginning of this week and all that. Okay, this is me factoring. Now what I need to do is apply this factor theorem to find the zeros. Okay, and here's how that works. This says that each one of these could be set equal to 0. So 3x cubed could equal 0. X plus 4 could equal 0. And 2x minus 3 could equal 0. And what I need to know is, what does that mean x equals in each one of those things? Well, in this one, and I'm going to try to do this without writing it all down, but we can always go back over it if you're confused. If I divided both sides by 3, I would still have a 0 over here. I would have x cubed equals 0. Take a cube root, you still end up with x equals 0. Okay, so this is 0 no matter what. X plus 4 equals 0. If I move that 4 to the other side, I get x equals negative 4. And if you think about that from this relationship, if my root is x equals negative 4, then my factor would be x minus negative 4, otherwise known as x plus 4. Okay, so there's that relationship. That was going from the factor to the root. All right. And then here, if I add 3 to the other side and divide by 2, I end up with x equals 3/2 or 1.5. And I don't want to take the time to do it, since you're watching a video, but I could now take this polynomial and graph it and just kind of visually verify that it crosses the x-axis in those 3 places. Okay, but the beauty of this is that now you don't have to graph everything to find where those intercepts are. Okay. Okay, moving on. This example 3, I actually think I'm going to skip over right now because we haven't talked about the type of factoring you would need to use to be able to do that. And I guess there is another way we could do it, but I think example 4 will make more sense next. So I'm going to go straight down to example 4. Write a polynomial in standard form with zeros 4, -7, and 1/2. Okay. I don't know if I'll take it all the way to standard form just for the sake of your time. But here's the idea. If you know what the zeros are, okay, if these are the zeros here, then the roots, nope, sorry, the zeros are the roots. I said the wrong word. Factors. The factors are always x minus the roots, okay, which is what I have over here. Remember, zeros is the same thing as roots. So if I know 4 is a 0, then I know x minus 4 is a root. Oh, I did it again. Factor. If 4 is a 0 or a root, x minus 4 is a factor. If 7 is a root, then x minus -7 would be a factor. And I'm actually going to just make that x plus 7 would be a factor. Now, this one's kind of weird. Remember this one up here where we had 2x minus 3 and it ended up being x equals 3/2? I could say x minus 1/2 equals 0. But when I throw that in as a factor, we don't usually factor with fractions like that, okay? So let's think about how we could write one kind of like this that would lead to a 1/2 as a final answer. And if we were in class together, I would, ask you to think about that. But really, if you think about it, if we put this 2 over here in front of the x and we make it 2x minus 1 equals 0, and we solve that, we're going to end up adding the 1 over here and then dividing by 2. And that would give us our 1/2. So instead of writing x minus 1/2 when it's a fraction, I'm going to slide that denominator over in front of the x. And that will work for you every time you're dealing with a fraction, okay? Because you're trying to make it so that it's a binomial that will work out to have 1/2 as an answer. So to get 1/2, I would say 2x minus 1. Okay. Now, the thing is, because this said standard form, technically what I should do now is multiply all 3 of these together. Like I said, for the sake of your time, I'm not going to worry about that right now. I did write all over my space where I was going to put my answer down, but I'll just squeeze it in here. So my polynomial would look like this. X minus 4 times x plus 7 times 2x minus 1. Okay? And this right here, just so you know, the way I wrote it just now, this is in what's called factored form. Standard form, if I wanted standard form, would mean that you actually multiply it all out and simplify. Multiply and simplify. I'm not going to bore you with that right now because I think that you guys are pretty good with the multiplication. The only time you would have to multiply it all out is if it required you to write it in standard form. If it doesn't say you have to write it in standard form, then factored form is totally fine and you could just leave it like that. Okay, so now the question is, how could we write a different equation with the same zeros? Okay, and this is kind of a weird thing here. So we want to be able to keep these 3 factors, right? Because we need to keep these 3 zeros. But if I throw a constant, if I throw a leading coefficient out here in front of this parenthesis, so let's say, for example, I put a 2 there, and then I go x minus 4 times x plus 7 times 2x minus 1, okay? That's technically a different polynomial. Like if I graph that, that's an entirely different graph. But this does not give me a different 0 because there's no x involved there. So it would still have these 3 zeros, but it just looks different on the graph, okay? And it is a different polynomial. If I multiplied it all out, this would end up getting a 2 distributed to everything. The other thing you could do is you could make it so that you have multiple copies of the same parentheses. So I could go like, you know, throw a square up there on the x minus 4, or I could throw a cube over here on the 2x minus 1. That leads to something called multiple roots, and we'll get to that eventually. But it would be the same root, just you have 2 copies of that root, okay? So those are some tricks that you can use when I'm asking you to write a different equation that has the same roots or the same zeros. Okay, that was kind of a lot. Going back to this example 3, then, I could apply something very similar to what I did here. I could graph this thing and use the graph to get the zeros. Okay, so I would get these numbers from the graph. And then once I have the zeros, I could turn those into factors. Okay, and that would probably be easier for this one than it would be to plow through it, you know, the way it's written right now. Okay, but we'll circle back to this one when I'm with you guys again. Okay, we'll do one similar to that. Okay, so just for tonight, what is it exactly that you have to do? And of course, once again, I don't have my homework packet here. Here we go. So one of the things I would like you to do tonight is this page that says factoring, putting it all together, okay? These are all going to be 2-step problems, okay? They are all 2-step factoring problems. Always start with GCF, okay? So this is just to practice factoring. This should definitely be done by Wednesday because that's when you're taking your quiz over all of this factoring stuff, okay? The other assignment is from the textbook, and that's over this new stuff, the Factor Theorem. That is listed on your homework tracker here. It's section 11.5 from your book. Okay, just a short assignment there. I will post the answer key as part of your blended lesson for tomorrow so you can see how you're doing, but we'll discuss this assignment when we're back together later this week. Okay? Okay, so homework for tonight, 2 things, section 11.5 and the pulling it all together worksheet out of your packet. All right, so it's this and this. All right, and I will plan to see you guys Wednesday. You are welcome to come see me tomorrow if you need help with anything.